And broadly speaking, it is a predictor-corrector approach, which attempts to estimate the state probabilistically of a partially observed dynamical system through a sequence of measurements. So we imagine that we have some statistical knowledge about the state of a system characterized by some probability distribution at time tn, and then by means of a model, we evolve that distribution forward in time. And then in principle, when we want to, when we observe, make an observation, we want to update the state using some basically version of Bayes' theorem. That would be the sort of theoretical gold standard of data assimilation. And the idea is that even if we start from a highly uninformative distribution in the beginning of the process, after sequential measurements, we can refine this, our posterior distribution, which is colored here in blue, and get a more accurate estimate of the state of the system, which can then be used for various sort of forecasting applications. So now, at least at a qualitative level, this sort of prediction correction approach, which sort of interchanges between continuous time dynamics and projective dynamics when observations are made, resembles some aspects of an extremely successful branch of modern science, namely quantum theory. So quantum theories have been developed historically to study physics at small scales, meaning subatomic or atomic scales, but their mathematical formalism extends far beyond that context. And in fact, some of the main contributors, like John von Neumann, have been active both in ergodic theory and in quantum theory. So in the quantum mechanical context, one replaces the notion of a classical probability measure that would appear in data assimilation by an object called the density operator or the density matrix. I will talk about this in more detail later on, but you can think of it as some type of operator theoretic generalization of a probability distribution. So in quantum mechanics, there is a unitary evolution that dynamically evolves these density operators, which are also known as quantum states, to future times. And this evolution is perfectly deterministic. And then when an observation is made, the quantum state, this density operator, is updated by some projective step, which basically is a quantum mechanical analog of Bayes' theorem, you can think of. And you get a new density matrix after a measurement. You may have heard a term like wave function collapse in popular language, which is used to describe this. So what we want to do, what we set out to do in this work is to kind of explore in a little bit more detail the connections between these two approaches, and in particular, try to cast the problem of data assimilation of a classical dynamical system, like in climate or weather forecasting, from the language of quantum theory. So here I will just give a brief overview of the approach. So what we consider is that we have some dynamical system that is measure preserving and evolves in some state space, which I call here M. And there is some invariant probability measure of the system. So we're going to adopt a operator theoretic description. So if you have attended Gary's talk, this was discussed extensively then a couple of days ago, looking in particular in the Koopman operator associated with this dynamical system, which is basically a composition operator acting on observables by composition with a flow. So for a measure preserving dynamical system, on the L2 Hilbert space of observable, there is a unitary evolution described by these Koopman operators. These are the adjoints of the transfer operators that, in this context, that Gary talked about. And what we imagine, we are doing data assimilation by observing some observable of the system, which I'm going to take here as a scalar valued, for simplicity, bounded observable. So if you want to have a mental sort of picture of this, I think Michael's examples from his talk fit quite well, at least from the, let's say, from the non-random case. I will just, we can just imagine that we have a dynamical system, which is, let's say, the Lorentz 63 system evolving in R3. So Rn could be R3. And there is an ergodic invariant measure supported on the Lorentz attractor. So you can think of mu as being supported on the Lorentz attractor. And in one of the examples I'm going to consider later on, we're going to think about a partial observation of this system would be simply observing, let's say, the x coordinate. So it would be taking the Lorentz attractor on the real line. And so if you are at a point, say, somewhere over here, you map under H to a point in the real line. So this would be some typical setup, if you want to have some concrete example in mind as I'm going through the talk. So I'm going to describe next how we can formulate a version of data assimilation in a quantum mechanical context using the Koopman operators that introduced previously, these unitary Koopman operators as basically an equivalent notion to the unitary operators that one uses in quantum theory. For those of you who have seen this before, these are basically what I'm going to state now are essentially a concrete realization of the abstract axioms of quantum mechanics as formulated by Dirac and von Neumann, using in this case the Koopman operator and the L2 space of observables to carry out the construction. So in particular, for a quantum mechanical system, one of the starting points is to have a Hilbert space, which is going to be used to define both the state and observables. Here we're going to take the L2 space as a sort of natural example, and we're going to define the state of the system. And when I say state here, I mean the state of the data assimilation system. You can think of this as statistical state as a so-called density operator, rho. And what a density operator is basically a positive trace class operator, which has unit trace. So in this context, you can think of the trace as being somewhat analogous to taking an integral in the classical probability theory. So this is somewhat analogous to having a so the normalization condition of a probability density. But now here we are in this sort of intrinsically non-commutative context, right? We are in this space of operators which can exhibit more general behaviors than classical probability distributions. And so we're going to use this as a replacement of the probability measure that one would use in Bayesian data simulation. And likewise for observables, we're again going to use a quantum mechanical language. Now in quantum theory, observables are not functions on a state space, but rather they are operators on L2, on a Hilbert space, which are self-adjoint. That's one requirement. And here for us, the natural setting is to consider self-adjoint linear operators on L2 as our quote-unquote quantum mechanical observables. Now, if you have a classical observable, like this observation function I was showing in the previous slide, you can map it into a quantum mechanical observable naturally by replacing it basically by a multiplication operator by that function. So if we have a function h, which is bounded, then this maps injectively into the space of bounded operators on L2, acting on other observables by multiplication. So this defines a bounded operator, which we're going to use as our a quantum mechanical representation of the assimilated observable. So now quantum theory next tells us how to evolve the state. So there is a natural evolution that acts on the space of density operators, so in the space of quantum states, which in this case we're going to affect using the Koopman operators on L2, or actually the transfer operators would be perhaps even more natural here, so the adjoints of the Koopman, which act on quantum states by conjugation. So basically, if you have a density operator, you can think of it as some type of infinite sized matrix. The dynamics act on this space of operators or matrices by conjugation in this manner. And that gives you an evolution that preserves the trace, the trace equals to 1 property. So this is a deterministic unitary evolution for these density matrices. Now, the next important ingredient from quantum theory, it tells us basically what we can expect from outcomes of physical experiments or physical measurements. So if you have a quantum observable A, so remember A is a self-adjoint operator on L2, quantum theory posits that the set of values that one can observe in a experiment that measures A is given by the spectrum of the operator. So the spectrum of the operator is a closed, of a self-adjoint operator is a closed subset of the real line. And so that consists with, basically agrees with the fact that physical observables are basically real values. And if you remember, when we are modeling, when we are describing our classical observable by means of a multiplication operator, well, in this case, the spectrum of a multiplication operator is nothing but the range of values that the underlying function takes. In this case, on the support of the invariant measure. So if I go back very quickly, so the spectrum here in this example, this badly drawn Lorentz 63 system, the spectrum of H, if it's measuring the x1 coordinate, would be something like some subset of the real line. So it would be some values that would basically correspond to all the x coordinates that you can observe from the Lorentz attractor in this example. Of course, other observables can have much more complicated spectra. So this is also consistent with what we expect classically. Now, what is more is that quantum theory gives us a prescription for how to compute probabilities of measurement, and this also fits very naturally with sort of statistical description of dynamical systems. Namely, if you have a quantum mechanical observable, so this is a self-adjoint operator, by the spectral theorem of self-adjoint operators, there is a so-called projection valued measure that allows you to decompose your observable in terms of this operator valued integral. So this is called a projection valued measure because it takes sets, it's a measure on the real line. So it takes Borel sets on the real line. Think of an interval, for example, as let's say a range of values that you could measure through using a detector of a certain resolution, and you want to find the probability that you will obtain a measurement within that range of values. So this is a measure on the real line, but it doesn't take values in real numbers like in classical statistics, but rather it takes values in the space of bounded operators on L2. So it's kind of like a non-commutative version of a real measure. And in fact, it takes values in the space of projection operators, orthogonal projections on L2. And there is a way of making this sort of formal integral that I wrote down here precise. So you can do some type of spectral resolution of your observable in terms of this projection valued measure. And if your system is in a state rho, and you want to find the probability of measuring A within a set omega, a Borel set omega, you can do this by applying this formula, basically computing this trace. And for a multiplication operator, this simplifies, basically it becomes the characteristic function that you get on the state space or on the attractor by pulling back omega along H. Okay, so so this is basically, we have a recipe for evolving the states and also a recipe for computing probabilities based on this. Now, the final ingredient is this quantum mechanical version of Bayes' theorem that basically tells you how to update the state once you've made a measurement. So once you have recorded a measurement for your observable, which remember it has to lie in the spectrum of your operator, there is a formula that updates the state to from its value immediately before the measurement to a state immediately after the measurement. This would be analogous to the Bayesian update in classical data assimilation, but here all the terms that participate in this expression are matrices or operators. Okay, so so basically, with all these ingredients put together, there is a self-consistent scheme that in principle allows one to carry out some form of data assimilation by applying these rules sort of sequentially every time that you measure the system. Now, you might ask at this point, why do we bother doing this? Because, you know, in some sense, this is a significant increase of at least mathematical or notational complexity. Well, one answer that I could give to that is maybe you're doing it because it's interesting. I mean, quantum theory is one of the most sort of deep theories that we have for the physical world. So I think it's intrinsically interesting to explore connections between it and other fields in statistical science and statistical modeling of dynamical systems. But I think there are also benefits in kind of like in a more operational or practical level. And one thing to note here is that, first of all, the sort of the quantum mechanical description of statistics is more general than the classical one. That means that if you have a classical probability density that evolves under some Liouville equation, this would be the generator of the for the Liouville equation, you can, in fact, you know, consistently embed this probability density into a quantum probability measure, like a quantum state, basically a rank 1 projection operator, and the evolution is going to be consistent, meaning that whatever the quantum, whatever probabilities your quantum formulation predicts for these multiplication operators that we talked about previously, they are consistent with what you would expect classically, so from classical expectation values. So basically, you're going to a bigger space than classical statistics. In fact, there are phenomena that it's not that every density operator in quantum mechanics has this form. There are phenomena in quantum statistics that do not have counterparts in classical statistics. And so by going to this bigger arena, so to speak, this gives you, at least in my opinion, some nice flexibility to ensure that certain conditions are satisfied by approximation schemes which wouldn't be easy or at least obvious how to enforce or immediate how to enforce otherwise. And one of these aspects that I want to mention here is that what happens when you look at finite dimensional or finite rank approximations of your system. In particular, when you want to solve this equation on a computer or you want to approximate it from data, typically you don't have access to these infinite dimensional spaces and these operators acting on them, but rather you have some type of finite rank approximations that are obtained, for example, by projection on a Fourier basis. So you could have an orthogonal projection that projects onto a basis that you're solving this PDE. And now, in general, if you have a function like a probability density, its projection on a finite, on a subspace is not necessarily a probability density. Even after normalization, it can take negative values. So that basically breaks some of the structural properties of the problem, namely that probability density should be positive. On the other hand, this is sort of very naturally ensured by if you use the quantum approach, because in this case, finite rank projection happens by conjugating an operator by projections, and this is actually positivity preserving. And similar properties hold in the case of observables. You naturally preserve things like signs of observables with this scheme. So one might say that looking at systems, the statistical evolutions of classical systems, which are projected in finite rank by finite rank projections, these could be said to be resembling more quantum mechanical systems, because now once you go to this projected space, there is no longer an underlying classical probability measure whose image is given by this operator. How much more time do I have? Sorry to.
I think around 5 minutes.
Okay, so I'm not going to discuss this, but we have a set of techniques that use ideas from kernel method for machine learning that actually allow you to implement this scheme to approximate it in practice if you have access to time ordered measurements of the system. Basically, in a nutshell, the idea is that you can construct data-driven bases for various function spaces of interest, in particular this Hilbert space that we want to construct our quantum mechanical system on. And then once you have a data-driven basis, you can replace all your Koopman operators or your measurement operators, density operators, and so on by matrices. So at the end of the day, the scheme becomes something like matrix algebra. And we can ensure, because of the way we set it up, that it has a well-defined convergence limit as you collect more data. So I'll give a couple of examples and one application from climate science in a very short amount of time. What I'm showing here is that we have a very simple dynamical system, which just corresponds to periodic rotation on a circle. So you could imagine your state space, in this case, is just a circle, and you have a particle going around this circle, and there is an angle theta that measures the phase of the oscillation. And here we happen to observe the cosine of that oscillation. So this would be our, h would project to the, basically just the x coordinate of this circle embedded in R2. So what this plot is showing is the probability distribution for h that this method predicts using basically this density matrix formalism. You can build at any time t, you can build a histogram about the predicted probability distribution for h. And so we start initially with a basically uninformative distribution. So it's basically a uniform distribution on the interval -1 to 1. And at this point here is the red line here indicates the truth signal. At this point, we make a measurement for the first time. Let me highlight it here. And once you make a measurement, of course, the probability distribution collapses down to a point, like kind of like a delta-like distribution. But then over time, you see it has this bimodal structure. And this is because when you have seen the x coordinate of an oscillation once, you don't know in which sense the oscillation is going, right? So naturally, you would predict a bimodal distribution. But then when another measurement is made over here, this distribution collapses to something which is highly unimodal and tracks accurately the true evolution. So this is just as a sanity check that in an extremely simple example, this is doing what intuitively you would expect. This is a slightly more challenging example, applying this for the x1 coordinate of the Lorentz 63. system, which now using this kind of like fully fledged data-driven approximation, of course, because we cannot do this analytically, where you see that this is in red here. I'm not sure to what extent it's visible through Zoom, the true signal and the measurements that are being made at different points, which are spaced by about 1 Lyapunov exponent of the system. So it's kind of like tracking the underlying trajectory, given observations of the x1 coordinate. And I'll just wrap up here very quickly. We now in current work, we're looking at applying this technique to performing data simulation of the climate system, in particular the El Nino southern oscillation. This is a oscillation that takes place predominantly in the Pacific Ocean. It's characterized by anomalies in the sea surface temperature that oscillate at a characteristic time scale of about 4 to 5 years, producing sort of global weather and climate impact. So this is a socially and economically important phenomenon, in addition to being very interesting scientifically. And what we do here, we take data from a climate model, so sea surface temperature data over the Pacific Ocean, and we use that to train, derive this in a data-driven manner, this Koopman-based quantum mechanical data simulation scheme that predicts these so-called Nino indices. These are scalar indices that measure SST anomalies associated with El Nino. And what, oh my, okay, my screen sharing froze, but it's okay. I will just talk and try to do it. So what you are supposed to see is that it predicts the probability distribution for the Nino 3.4 index in at least in this model. This is sort of a diagram where, as you go down in time, the lead time of the forecast increases, and in horizontal direction you have the verification time of the forecast. You can see basically from short times to late times, you have a gradual increase of uncertainty, as you would expect around the truth signal of the Nino 3.4 index, but otherwise it is tracking fairly successfully. So I'll stop here. I'll just leave this slide, and thank you very much for your attention.